The name of the problem is Towers of Hanoi. You might have heard about it. It is about having three pegs, F and S and T. You can name them first and second and third. And then you have N disks on top of the first peg, which you want to move all of them to the third peg. And the way you can do that one, you have two restrictions. First of all, on each move, just one disk, only one disk could be moved. And restriction number two is there shouldn't be any point of time that a bigger disk should be sitting on a smaller one. Like as an example, in my example, I have just three disks, 1, 2, 3 from top to bottom. So 1 is the smallest, 2 is the mid one, and 3 is the biggest, right? So there should be no point in time that, for example, 2 is sitting on top of 1, or 3 is sitting on top of 2 or 1. It should be always like this, from top to bottom, from a small to big. Is it clear? Now, doing it manually, let's say N is 1. Let's say I have just one disk. How many moves do I need to have? Just one move. Basically, F is the first peg, T is the third one. So you want to move N disks from first to third with the help of S. So S is the secondary or the helper one. If N is 1, you just do it as the one on F goes to, let's say, I really like this. The disk I have on top of peg F goes and sits on top of peg T, like this. And at the time I have just one disk, I move it from F to T. Then what if N is 2? Now assume we have two disks on top of the F, and we want to use S to help us move both of them to the top of T. So we can say F goes to S. What I mean by this is what is on top of F sits on top of S. Now the mid one is still on F. F goes to T. Now what you have as the first one, number 1, goes from S to T. Is it clear? Yeah. Now let's say N as 3, which is what we have in here. If N is 3, probably you can imagine, it's not hard to imagine, F goes to T this time, then F goes to S. So the first one, the smallest one, goes to third. The middle one goes to second. Now you have the smallest one on third. That goes to second. Now you have the biggest one on F. It goes to T. Now you have the middle one on S. It goes to F. Now you have the smallest one on S. It goes to T. Now you have the smallest one on F, which goes to T. Yep. Did you understand the problem?
No, the third scenario.
Did you understand the problem?
Yes, sir.
Okay. So we have three disks, and these three disks want to move from F to T. I bring the smaller one to third. I bring the middle one to S. Okay. Then I bring the smaller one to S. So now the smaller one is sitting on the middle one. I bring the bigger one to third. I bring the smaller one to F. I bring the middle one to T. And I bring the smaller one to T. Yeah. If you understand the problem, it shouldn't be hard. You have these number of movements, and in each movement, there shouldn't be any bigger disk sitting on top of any smaller one. Okay. Now, if you look at the number of and you can continue like this. You can do this one for N as 4, N as 5, N as 6. The first time I faced this problem a long time ago, and I had learned just to program with it was GW Basic, I believe. And I didn't know anything about recursion, so I had to find some pattern to solve this problem. The pattern you can find here is, for example, look at this data that we have. I remember I did it on paper for 6, N as 6. 1, 2, 3, 4, 5, 6. If you look at the pattern for N as 1, how many steps you have? Just one. You can write it as 2 to the power of 1 minus 1. If you have N as 2, how many steps you have? You have 3 steps. So you can write 3 as 2 to the power of 2 minus 1. And if you have N as 3, you have 7 steps. And then you can write 7 as 2 to the power of 3 minus 1. You get the idea? So probably you can guess if you have n as n in general, then you're going to have 2 to the power of n minus 1 steps. That's the first thing. The second thing you notice here, when n is 1, when n is 3, and if you continue when n is 5, when n is 7, the first move is f to t. But when n is even, like when n is 2, and you can continue when n is 4, and n is 6, the first move is f to s. And this is something like finding these patterns takes some time, so you can continue on your own. Again, the same way I did long time ago, you can draw those moves or write those moves for 5, for 6, for 7, and then based on them, find some patterns and then come up with the code. I'm going to let you know it's not going to be easy. It's not hard, but it's not easy as well. The easiest way, as opposed to many think, is the recursive solution. The recursive solution at the beginning seems to be hard, but I'm going to explain this one with the easiest way I can. Remember yesterday we talked about that quote in the notes that says, recursion works by magic. There is some magic behind the scenes that's happening. If you want to think about recursion, if you see a recursive code and want to think what's actually happening, it could be driving you crazy. But I'm going to let you know there are some easier ways to think about the way you can even implement recursion on your own. So I'm going to talk about that magic behind the scenes today. And luckily for you, we don't have to prove them mathematically. We can just accept. You can't just accept whatever I say today. You can think about whatever I say today. You might want to really understand why the things I'm saying today are working. But it will take some time. It will take at least some hours from you. And probably you don't have that time. It's up to you anyways. I'm just giving you the conclusions, the mathematics behind the scenes, that why this is happening to be like this. So first thing first, remember yesterday I talked about factorial and Fibonacci, and I told you that I don't like those problems as recursions because you can turn them into iterative version easier than recursion. But for this one, as I told you, you can find patterns, but finding all these patterns takes some time, which is going to be harder than thinking about this same problem in a recursive way. So how you can solve recursion? First of all, you remember for all recursions, you need one base condition, right? And the base condition says if the problem is as small as possible, so small such that it can be solved very instantly. In this example, if n is 1, that's the smallest case possible. And you have just f to t. By the way, this is the way I'm printing things. You can be more specific in the printout of your program. You can say, move disk number 1 from f to t, something like that. But this is the succinct way I'm using. F to t, f to s means whatever you have on top of f goes to t, so on and so forth. If n is 1, that's the smallest case problem. You just take whatever you have on f, you put it on top of t. This is the small case. This is the base case condition. What about the recursive itself? So if you look at the drawing I have in here, by the way, I'm just reusing these slides from previous semester's basically lecture because just to save time, just to have more time to talk about lab 2. So I'm reusing them, not to draw them from scratch. So the way you can look at this thing recursively is, I can say I have n disks on top of f. What if I take the topmost n minus 1 disks from f to s? So assume that with some ways I have been able to move the topmost n minus 1 disks from f to s. This is what I call a step number 1. Step number 2 is so easy. Now I'm left with just the biggest one in here. I bring it from f to t. And then a step number 3 is the same way I brought those topmost n minus 1 disks from f to s. I'm going to take them from s to t. You see the recursion in here? I changed the problem for n to be solved for n minus 1. Now, the way to take n minus 1 is still a problem, but at least I was able to express the solution recursively. Yeah, this is basically what you kind of name it as divide and conquer. So you divide your problem, you basically split your problem, like you turn the problem for n to n minus 1. Now the thing here, which is nice, is when you turn your problem for n to n minus 1, the problem for n minus 1 is still the same problem. If you don't know how to take n disks from some peg to some other peg, the same way you don't know how to do n minus 1 disks, right? But at least I was able to turn the solution for n to a solution for n minus 1. But for now, just bear with me. I have 3 steps. Now, I have 2 good things. First, I have found the base condition like n as 1 in this problem. I have found a formula to turn n to n minus 1. Again, I can't say I have solved the problem, but to be honest with you, and back to the quote that recursion works by magic, that's the end. If you are able to find the base condition, and if you are able to turn your problem of size n to some smaller size, like in this case n minus 1, in some other cases could be n minus 2 or whatever, then basically you're done. Let me show you how. And this is the part that magic happens. Let's say I want to turn these steps 1, 2, 3 into a code. And I know n as 1 is the base condition. What I can do is as easy as this. First of all, let's talk in terms of Python. I write the definition of my function like this. Definition Hanoi, how many parameters I need? I need 3 parameters for pegs, f and s and t, because I need to be able to look at the printouts. I need to be able from which one to which one. So I need 3 pegs. And then the 4th parameter is the most obvious one, which is n, the number of disks. And then based on this, I would say first the base condition. If n is 1, print f to t. So far so good? Everybody's okay? You had your coffee? Okay. So print f to t. Otherwise, no, this is nice. Otherwise, you have to follow all those steps. Step number 1, then a step number 2, then a step number 3. Now, this is the part that, again, I'm trying to make it as simple as possible for you without going into the details, all the math in the background. You can't think about it, why this is correct, but this is always correct, and this is magic. Seems to be at least magic. Now I'm in the middle of writing my function, right? I haven't yet done implementation of my function, but I can assume my function has been written before. That's the magic. I haven't yet done the implementation of my function, but I can just imagine my function has previously been implemented. Based on this, what does my function do? Takes n disks from f to t with the help of s, right? What did you want to do in step number 1? You want to take the topmost n minus 1 from f to s. If this is the function that takes n from f to t, how should I call this one that does the same job for n minus 1 disks, but from f to s? Any suggestion?
The variables.
Just, yeah, guys, to be honest with you, the whole art of recursive programming is playing with these parameters. Just the way you swap these things over and over and over. So how do you express that one? Step number 1, the same thing you said. You call Hanoi, but we know this takes n from f to t. We say call Hanoi, but take from F to S, n minus 1. This is super nice. We haven't yet done the implementation, but we can assume we are done with the implementation and then use it as part of the implementation. This is the magic one. So step number one, which I have in the comment, step number one can be implemented as I call Hanoi, I take n minus 1 disks from F to S with the help of T. This is step number one. Step number two was so easy. Remember what that was? Take the biggest one from F, bring it to T, because on the F you have just the biggest one. On the T you have nothing. So we say print F to T. This is step number two. And then step number three was the same n minus 1 disks should be gone from S to T. Look at this. Call Hanoi again, n minus 1 disks from S to T. These red statements, I wrote them because I assumed I'm already done with the implementation. And now that I wrote all those, I'm really done with the implementation. That's the magic. This is the way you can think as easy as possible. You can, as easily as possible, you can think about recursion. Now, if you are a person that sees this code for the first time without all these explanations, and then you want to trace this on your own, it's going to be so hard. It's like me the first time, long time ago, after I discovered there is a recursive solution. And I didn't even know back then that what is recursive. And then I want to go over this one to see what's happening. And then you think the person writing this one should be a genius. But they are not. Basically, I will tell you, writing this one is much more concise and much easier than if you want to do the same thing iteratively. So at the beginning, recursive might be hard for you. With a bit of practice, it should get easier. And this is the way you can think as easily as possible about the way you can implement a recursive function on your own. Just note that how did I do steps 1 and 2 and 3? I did it based on the fact that I assumed my function is already working, so I just used this knowledge to call these functions in steps 1 and 3. This is one of those recursive implementations that each time it 2 times calls itself. It's like Fibonacci. If you do Fibonacci on the recursive way, this is the same thing. Not like factorial, with just factorial n reduces to factorial n minus 1. This time for n, we just call Hanoi 2 times. And this is what's going to be make it even more worse, even worse than what we had in the case of factorial, because I'm going to show you. I don't even need to show you. I showed you before. What is the order for n disks? It's 2 to the power of n. So it's big O of 2 to the power of n. We talked about that before. This is one of those worst cases. So this code that you see as recursive, you can run this code, it works for all n's. But the problem is, if the n is getting bigger and bigger, now you're going to have a large gap. You should wait for sometimes seconds, sometimes minutes before it starts running because of the runtime stack. And sometimes you might get a stack overflow. But that same thing doesn't happen. If you implement this same thing iteratively, you pass n as 1000. Who cares? This is the advantage of iterative over recursive. But what is the advantage of recursive over iterative? We could implement this one very instantly. And if you know this magic which I told about regarding recursion, your implementation doing this recursion is much more easier compared to if you want to do the same thing but iteratively. Okay, so let's continue. First of all, I think I have the code for you in the same core folder of teaching and learning Python, which I talked about it before. You already have access to this one. I should have recursion, which I have. And then I go to Hanoi, and let's say this is Hanoi.py. And I have these multi-line comments. I talk about this again because you need to have comments in your code for assignment one. You need to have a multi-line comment expressing the parameters, the functionality, whatever for your function. And not only that, but also you need to have single line comments for any any place in code that needs to have some comments. For example, I have said base cases. If n is less than or equal to 0, just return because it doesn't make any sense. If n is 1, print. Now, this is a bit more verbose. Move disk n from f to t. And I've used formatted string. We talked about this one before, right? And then return. Otherwise, now we go to recursive case. And first, you move the top n minus 1 disks from f to s with the help of t, which is like this. The same thing we talked about. Then you move the biggest disk from f to t like this. And then you move the same n minus 1 disks from s to t like this. You can run this code. And just for your information, because I remember previous semester, some students liked to compare Python versus JavaScript versus Java, because these are at least my topmost programming, like favorite programming languages. So same in JS. You can have a look at this one. The same way we can do this thing in JS. And at the same time, by the way, this is just some other way. If n is bigger than 0, do this. Or if I want to have that one the same way as it was in the Python case, or look at this. The same way, if you like to compare that one with this same code in Java, just for those of you who like to compare, you can have a look at this one. These are just different syntaxes, just to make you familiar with the way these three big programming languages work in general. But let's focus on the Python one, which is the tool we use in this course. This is the whole thing you need. This is the solution. You can run it. And then this one takes an n as an integer and then calls the Hanoi, and you see all the outputs. So I will let this one to be run by you on your own. Let me get back to here. Let's see how to trace this code. The way you can trace these things is by drawing call trees. So call tree, what is a call tree? It's like a tree which starts from the main call. It starts with the main call and then goes all the way down until you hit a leaf and then you return back. So if you're familiar with the concept of backtracking or depth first search, this is kind of the same thing. You start from the main call, you go down, you go down, you go down until you hit the base case, then you get back and then you take another branch. So that's why it's a call tree. Let's say we have started with calling Hanoi with character f. In Python, it's best to say a string f as f, string s as s, string t as t, and 3 as n. Note that here I have said f and s and t. Here I have called f and s and t. These are different. These f and s and t, these are parameter names, but these ones are the actual strings being passed to them, right? And as I told you along the way in recursion, these things get swapped over and over and over. Now, what I'm trying to do in this green slide is I'm trying to depict the call tree starting with the main call, which is, let's say we have assumed that we have called Hanoi with f and s and t, the value 3 for n. How do I do that one? Remember, what did I have? It said if n is 1, just print and done, else do this. Now I'm inside the else because n is 3. The first thing I should do, I should call Hanoi, f and t and s and n minus 1. What is different, guys? From the base call to this sub call, what are the differences? N has turned to be n minus 1. This was f and s and t. This has become f and t and s. So the second and the third parameter have swapped. That's why when you go here, you see that I have said this one results in f and t and s and 2. And again, n is not 1 yet. So you have to do a second recursive call. So again, you call this function, this time with n as 1, and you call it like this. So n is 2, you go inside the else, you call Hanoi, f and t and s and n minus 1 again. So it leads to going from here, we go here. It's going to be f and s and t and 1. Again, I changed the second and third, and then I reduced n by 1. So far, so good? Now, this is n as 1. When n is 1, you just print f goes to t and you return. What is f? What is t in here? F is f, t is t. I print f to t and I return. This is the first thing getting printed. Then I go back. It's like a backtrack because I have reached a leaf in this call tree. I go back here. When I go back here, I'm in the second line of else. I print f should go to t. But in this case, f is f, t is s. So the second thing getting printed is f to s. I'm done with the second. I'm going to call this nested recursive call. Call the Hanoi, s and f and t and n minus 1. Now comparing with the main call, if this was f and s and t, this one is s and f and t. Means the first and the second argument are swapped and n is reduced to n minus 1. So we go here. It is f and t and s. We change it to t and f and s, and 2 becomes 1. Hopefully you are following. Then it prints f to t. Here f means t, t means s. So the third thing getting printed is t to s, and then I return to here, and then I return to here. Now at this point of time, I'm back to my first main original call, and in that call, I already have done a step number 1. Now I do a step number 2, which says f to t. And in step number 3, I print f to t. F is f, t is t. So I print f to t. Then I will do call Hanoi again. This time again, the first and the second parameters are swapped, and n becomes n minus 1. So I go here. I call Hanoi again. Now s and f are swapped. T is not changed. 3 becomes 2. Again, n is bigger than 1. So I call again a recursive call. Now I get into the else again because n is bigger than 1. Again, second and third are swapped, like I'm talking about this one. Second and third, like s and t and f, like this. 2 becomes 1. Since n is 1, I just print s to f because f is s, t is f, and I return. When I return back to here, I print f to t again because that's the second thing. F to t is getting printed as s to t because f is s in here. And then the last thing which is done is I call it again with s and f and t. It means the first and the second are going to be swapped. So it's going to be f and s instead, and t and 1. And now you're going to be printing f to t and return and return and return and done. You printed 7 things, and if you compare them with what we had in the first slide, those are exactly what it should be. And probably you can admit that even tracing this one was harder than writing the code itself. And that's the magic behind the recursion, if you have got recursion correctly. I know it's hard, I know it's confusing. What you can do, just practice, practice, practice. Half an hour a day. It doesn't suffice? 1 hour a day. You need more? More. You need 1 more semester? 1 more semester. But you need to learn it, right? And remember, recursion is one of those things that you're going to need even in the second half of the course. So make sure you understand it. And this is the same reason I'm recording this one. Hopefully, it's getting recorded in a desirable way such that you can rewatch it, you can rewind it as many times as you wish because it's what you need. Okay? Now, based on all this, what I'm going to do is I'm going to give you some exercises. Okay? Exercise number 1. Remember, I told you this same thing could be done iteratively. So, the same way I did it for n as 1 and 2 and 3, do this same thing for n as 4, n as 5, n as 6. It's going to be a lot, I know. For example, when n is 6, it's 2 to the power of 6 minus 1. It's 63 steps that you should do on paper.
For 15, it's 32,007.
For 15, don't even talk about that. Okay, so do it on paper and then compare and then bring all those patterns together to write it iteratively, to implement that one. I just want to show you one fact that although many of you think that recursion is hard, I just want to show you something that when you try to write this code iteratively, this is much easier. And the way we explained it, the way I talked about that one makes it even much more easier compared to the same thing if you want to do that one iteratively. Exercise number 2. The same way I did the call tree for 3, this is even more important. Draw the call tree, do the call tree for n as 4. Just make sure you understand what's happening. For n as 4, that would be 2 to the power of 4 minus 1. It's 15 steps. It's not going to be hard. But draw the call tree because drawing this call tree is what you need to understand recursion correctly. So make sure you do that one. Exercise number 3. As you see, recursion is the art of first, coming up with the base condition. Second, the art of seeing the way we can express our problem recursively. In this case was steps number 1 and 2 and 3. Third, the art of understanding how many parameters do I need. For example, in this case, I needed 4 parameters, not more. Now, I want to give you an exercise which is like factorial, which is like Fibonacci. It's not even needed to be done recursively, but I like to ask you to do it recursively, just as a practice on recursion. Assume I have a function which receives a string and reverses that. We already have talked about reversing a string. In Python, it could be done so easily, right? But assume you don't know slicing and all those things like that. You don't know anything like dot reverse function. You have a function which receives a string, and then you want to reverse this string recursively. Think about that as an exercise and follow the same thing I talked about in here. The most magical part was the else part in here, which when you get into the else, those red lines, we talked about it, that you can assume that your function is actually working, and then you call that because that's the essence of recursion. Okay? So make sure you do all this like these exercises. These exercises don't have any marks, but they're going to be helping you learn more about and practice more on recursion. Because at the end of the day, you not only need to understand recursion, but also you need to implement recursion like this. And most importantly, you need to be able to trace recursion like this. So if some of you have a question that I didn't get it fully, that's natural. We have some friends of you which didn't get anything because they joined late, right? It's so natural. But it's not going to be natural 2 weeks from now. Even next week, you should have tried this on your own. And then you should practice on your own. Any questions? Get back to me. If you can't draw this call tree on your own, there is some problem. Again, this was the first time, and fortunately for my friends who joined late, we are recording this one just exceptionally in the labs. We are recording because I know this part is very important. And later on, you can rewatch this one over and over and over. And just make sure you understand this, the whole thing before next week. Because as I told you, you always need to understand recursion, implement recursion on your own. And if we give you a code like this, you need to be able to draw or produce this call tree on your own. Any questions for now before I end the recording? Because this was the part I like to record. Hopefully it got recorded as I expected because I'm using the mic from the laptop. Probably the sound quality might not be that good. But anyways, at least you have some way to rewind or rewatch that one.